Valence Bond Theory. The Lewis model is very nice and simple, but it's an oversimplification. And so more robust theories apply quantum mechanics. And the quantitative approaches involve some really hairy math. But they're able to accurately predict lots of properties like bond length, bond strength, molecular geometries, dipole moments of molecules, all this great stuff. We're not going to look at the quantitative aspect of this. We're going to look at it in a qualitative manner. So we can be very thankful for that. So quick review. Electrons reside in quantum mechanical orbitals that are localized on individual atoms. And we talked about these as S, P, D, and F. And we talked about them as regions of probability of finding an electron. We also discussed the wave-particle duality of electrons, and that basically these orbitals are like standing waves. What valence bond theory brings in is that you can hybridize atomic orbitals, blending two or more regular atomic orbitals to make a new kind of orbital. So in the quantum hotel, I talked about these different sub-levels as being the rooms in the hotel. And in the P room, there were 3 beds, and the beds were the orbitals. So the hotel analogy of this is you could take the S room and the P room and break the wall down in between, and now you could advertise the 4 beds in this expanded room as SP3 beds, because they're from the S and the P. So if that gives you kind of a clue as to where we're going. It probably doesn't, but that's okay, I said it. So the idea here is that when 2 atoms approach each other, we've got the electrons and nucleus of one atom interacting with those of the other atom. The nuclei repel each other, the electrons repel each other, but the electrons of one atom are attracted to the nucleus of the other. And so if they come together and the result is a lowering in energy, you get a bond that forms. The valence bond theory is looking at the energy changes. So here we have a graph where energy is increasing positive, and remember, positive energy is unstable, more negative is more stable. So if you think of a ball rolling down this hill, where's it going to end up? It's going to end up down here, right? It'll settle down here. The lower energy. Just like balls rolling down hills, these atoms are going to interact in a way that gives them the lowest energy. So here we have 2 hydrogen atoms approaching each other. As they get closer, the electrons of one are attracted to the nucleus of the other, and so there's a lowering of energy because of that attraction. At some point, we reach this minimum energy, and then if we push them together, they start to go up in energy again. So if we think of these as 2 people, and so you see someone across the crowded room, right? Like I saw Kirk across the crowded room earlier. It's like, oh, I'm attracted to him. As you get closer, you get more and more attracted. You can see that person more clearly. And then you get to this point where you can converse easily, and then that's good. But what if you're talking to somebody, you really like them, but they're one of those people that doesn't understand personal space, right? And they're getting a close talker, right? And they're just getting too close to you. Is that attractive? No. And then you're like, ew, get away from me, right? So, occasionally. Occasionally. So as they approach, the attraction is greater and greater, and then when they get too close, they start to repel each other. And so they're going to end up at this ideal distance, which is the lowest energy. And all of that can be calculated. The energy here corresponds to the bond energy, and the distance corresponds to the bond length. That's that bond length is where it's most stable. So that interaction is stabilizing, it's negative. When you have atomic orbitals that interact, so you've got an overlap of 2 atomic orbitals, and we've got a pair of electrons in the overlapped orbitals. They can spin pair. So you'll have one spin up and one spin down. Usually the two electrons in that overlapped orbital are going to come from two separate orbitals. One electron from one atom, one electron from the other. They would each have a half-filled orbital. Those half-filled orbitals will overlap, and then the electrons can pair. But sometimes it's called a coordinate covalent bond. Sometimes an atom will use a full orbital, a filled orbital, and overlap with an empty orbital on another atom, and they can form a bond that way as well. That's much less common. So the idea here is that the valence electrons are in these quantum mechanical orbitals, and a chemical bond happens when you have two half-filled orbitals, one in each atom, that overlap, and now we've got a pair of electrons in that overlapped orbital. The geometry of the overlapping orbitals is what determines the shape of the molecule. Any questions so far? Okay, so let's look at carbon and, oh, that's not carbon, that's sulfur. Never mind. Look at sulfur and hydrogen overlapping. I said carbon yesterday, and nobody corrected me. So here is a valence orbital diagram for sulfur. Everybody okay with that? It's got 6 valence electrons, 2 in the 3s orbital, 4 in the 3p orbital. There's going to be 2 orbitals that are only half filled. Here are the orbital diagrams for hydrogen. So we can get the hydrogen's half-filled orbital overlapping with a half-filled p orbital for sulfur. And we can have the same thing happening with the other hydrogen overlapping here. And we get H2S would be the formula for the molecule. So here's the hydrogen. It's contributing one of these electrons, and this sulfur's half-filled p orbital is overlapping, contributing in another, and there's a lowering of energy, and so a bond forms. And here we've got another p orbital, and then the third p orbital on sulfur is full, and so that's got a lone pair. Everybody okay with that? Half-filled orbitals overlapping. Well, we observe that the actual bond angle is 92 degrees, but valence bond theory, this valence bond theory predicts that it's 90 degrees, because what's the orientation of those p orbitals? They're at right angles to each other along the x, y, and z axes, right? So we would expect right angles there. Vesper theory predicts, based on lone pairs and things, that it would be less than 109.5. So our valence bond theory here is doing okay. Now let's look at carbon. So here's carbon's orbital diagram. It's got 4 valence electrons, 2s2 and 2p2. So we've got 2 half-filled orbitals, and here's hydrogen. He's always the same, 1 half-filled orbital here. And so we could see how this orbital could overlap with one of these, and then another hydrogen overlap with one of those, and we could get something that looks like this, right? Half-filled orbitals overlapping. This would have a bond angle of 90 degrees. And what would the formula for that be? How many carbons are in there? 1 carbon, and how many hydrogens? 2. So that would be CH2. But that's not what actually happens. Carbon forms bonds with 4 hydrogens. And so we get methane, CH4. CH2 does not exist as an individual molecule. Like, oh, that looks funny. Why does that look funny? Our valence bond theory here would predict a bond angle of 90 degrees because you've got 2 p orbitals overlapping, right? But the actual bond angle is 109.5. We have a problem here, more than one problem, right? So we have to adjust our theory. I'm squishing 2 sections together. Oh, well. Okay, so atoms have these orbitals, right? But what's to say that those orbitals maybe get changed a little bit when it interacts and becomes part of a molecule. So we call this hybridization. The orbitals are mathematical functions, and you can combine the mathematical functions. Now, exactly how we do that doesn't matter. You can think of it as averaging, right, in a simple way. So we're averaging those standard atomic orbitals to make hybrid orbitals. This is where you're taking the S room and the P room and you're breaking the wall down and you're remodeling. Okay? You're going to make a new kind of room. So this hybridization corresponds more closely to how the electrons are actually distributed in molecules. They're still localized on the atoms, but they have different shapes and different energies than the standard orbitals. By hybridizing, we can minimize the energy of the molecule by maximizing the orbital overlap. So you can get better orbital overlap. And this is, we're not doing this to molecules. We're trying to tweak our theory so that it matches up more with what we actually observe. So the orbitals are going to have better overlap when they're hybridized because the electron probability density gets more concentrated in a single direction instead of being spread out on both sides. Hybridization does require energy. If you're going to remodel that hotel, you're going to have to invest some money, right? But you hope that there's a payback later. So the hybridization only comes when there's enough energy payback from forming bonds to pay for the energy required to hybridize. So what we're going to look at is a simpler version of valence bond theory. We're only going to look at the interior atoms being hybridized, and we're going to assume that the exterior or terminal atoms are unhybridized, and that's just going to simplify things a little bit. So when we talk about hybridization, the number of standard orbitals added together always equals the number of hybrid orbitals. If you start with 3 orbitals, you end up with 3. They're just different. So if I'm remodeling, and I start with 2 beds, I'm going to end up with 2 beds. No beds are created or destroyed in this. No orbitals are created or destroyed. They're just modified. So the number has to stay the same. Which standard orbitals you add together determines the shape and energy of the hybrids. And the particular kind of hybridization is the one that's going to give the lowest overall energy. Those calculations way too complicated to even talk about. So what we're going to do is we're going to use Vesper theory to predict the geometries. Well, the Vesper theory is going to help us predict the electron geometries. That's not what I meant to say. We're going to use the geometries from Vesper theory to predict how it hybridizes. So here is standard atomic orbitals for carbon. We've got an s orbital and 3 p orbitals. There are 4 valence electrons, so 2 would be here, and these guys would be up here, each in their own orbital. Hybridizing, we're going to take all 4 of those and mash them together, average them, hybridize them. So the p orbitals were higher in energy and the s was lower in energy, but when we combine these, the energy of the 4 is going to be the same, and it's going to be between what it used to be. So it's some sort of average. Does that make sense? So it's higher than the s and lower than the p. We say those orbitals are degenerate. They're the same. Yes?
Does hybridization somewhat explain / have to do with how many bonds molecules like to?
Yes. The hybridization very definitely has to do with how many bonds a particular element likes to make. So in the carbon atom, there was a pair of electrons in the 1s and 2 unpaired in the p. Question?
Is this why we calculate we're actually trying to calculate based off of that, the valence electrons, when we include it 2s?
Yes, this does have to do with why are the 2s electrons considered valence electrons and why are they participating in bonding? Because they actually are. the 2s and the 2p orbitals are going to combine together to make 4 hybrids, right? And then because these all have the same energy, the electrons aren't going to be paired up. They're going to each take their own orbital, right? We learned that when you fill this up, you go single, 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 and then the next one has to come in and pair up. Well, here they can all have their own bed.
Where does the 3 come in?
That's a good question. Where does the 3 come in? So sp3, it's because there's an s and 3 p's. So we took s, p, p, and p. So it's like p cubed, right?
So you're pulling one electron from the S and breaking the other electron from the S into the 3p.
She's drawing.
I'm drawing, and I'm sorry, this is very difficult. It has to be on my left hand, but I can't write with my right hand.
Really?
I'm a left-hander. Just,
You're left-handed?
yeah.
I hadn't noticed either.
That's why I keep writing with my left hand. That's why I have my iPad upside down, because it's
Oh, I
wrong.
thought because you needed the mic closer to your face.
No, the mic's up there.
Yeah, I was thinking closer to your face.
She's writing with the left hand.
Whatever. Anyway, okay, so why am I writing my fingers? S, a P, and a P. Okay? S, P3.
S kicked that electron out to the P.
What happened to what? Well, this one didn't have any Ds. There's no D orbitals on a carbon. I need to grow 2 more fingers. We'll get to the Ds. Okay. So, pictures. Okay, so here's an s orbital, spherical, and there's our p orbitals. They're like these lobes. And this is like a standing wave, remember, with a node in the middle. And here's a standing wave. It's just oriented differently. So we're going to take all 4 of those and average them together, and these are the 4 equivalent things we come up with. So there's still 2 lobes, but now one of them is definitely smaller than the other. That's the influence of putting this sphere in there. This doesn't have one side or the other side. And so you end up with one big side and one little side. And now these 4 things are going to orient themselves in space. They're going to spread out. The reason that the p orbitals are at the x, y, and z axes is because that's how they have the most space. But now you throw another one in there, and you've got 4, and what do 4 things do? Tetrahedron, right? So these are going to make a tetrahedron. So here we're showing all of them together. Now what we don't show here is this little lobe. Okay, this is like a little stub over here. It's there, but it just makes all the drawings more complicated, and we don't want that, do we? So it's there, but it's not very important. So we're just going to look at the big lobes, and so they make a tetrahedron. So now each of these hybrid orbitals, sp3 hybrid orbitals, for carbon is going to have 1 electron in it, and it can overlap with a half-filled orbital on hydrogen. And it can do this. So remember hydrogen, our little friend. Hydrogen has this s orbital that's half-filled. So 1 hydrogen overlaps with this hybrid orbital, another one with that, another one with this, another one with that. So those sp3 orbitals are arranged in a tetrahedral shape. They overlap with the hydrogens, and the resulting molecule has a tetrahedral shape. So now our theory is matching up with our observation. Any questions? And this is why carbon forms 4 bonds.
Are those pi bonds?
These are sigma bonds. Yeah. Any other questions? We can have lone pairs. You can have a lone pair in a hybrid orbital as well. So if we look at nitrogen, nitrogen's atomic orbitals, well, those came out really small. How many valence electrons does nitrogen have? 5. 1, 2, 3, 4, 5. So this is P and this is S. And it, am I what?
Oh, there it is.
It says at the top, sorry. It's very small. I should have done it differently, but I didn't. It's too late now. So if we take those 3 P's and an S and hybridize them, it's called sp3. And now put the 5 electrons in. 1, 2, 3, 4, 5. Okay, so nitrogen has 3 half-filled orbitals that it can overlap with hydrogens. So here's one of them, making a bond with hydrogen. Here's another one. Here's another one. And the last one, or the first one, depending on your point of view, is a lone pair. And this matches up with what we observe for the ammonia molecule. Its electron geometry is tetrahedral. The molecular geometry is trigonal pyramid. And here we've got this lone pair taking up a little more space. So it's going to push these guys together a little bit. Any questions?
When we're trying to figure out the hybrid orbitals, doing the SPDF, we're not going based off of like how we did the electron configuration. It's just
We're going to predict the hybridization based on the number of electron groups on the Lewis structure.
okay.
So we're basically using Vesper theory to tell us how to hybridize it. Because otherwise it's way too complicated. Do you have a question?
Yes, that orbital, the sp3 orbital,
Mm-hmm.
it is titled the same for both nitrogen and carbon, even though there's a different number of electrons?
An orbital is given a name not based on how many electrons are in it, but based on what it's a combination of. So these are sp3 orbitals because it's one s orbital and 3 p orbitals averaged, if you will. And so we still have 4 orbitals. They're called sp3 now. And you just fill them up just like we filled up the atomic orbitals. Doesn't matter. But the number of valence electrons affects how many of these will be full, and that affects how many bonds this thing's going to make. It's, when you see it, it's so awesome.
So that's what it's saying, the Lewis dot structure is an oversimplification because this is like
Right.
the consult direction of this.
Yeah. But what's really neat in sort of a coincidental way is, when we drew Lewis structures, right? We told you to do like this, 1, 2, 3, 4, and then you have to pair up. Well, that kind of inadvertently corresponds to this. Okay, let's look at sp2 hybridization. So here are our standard atomic orbitals. What if we take the s and only include 2 of the p orbitals? Well, we're going to have 3 orbitals that are intermediate in energy between the s and the p. And what happens to this guy? Nothing happens to him. He's just sitting over here, same as he was before. So this is an s and 2 p's, right? So sp2 hybrid orbitals. What would these look like? Well, here we take an s and 2 of the p orbitals, and you mash those together. You get 3 of these hybrid orbitals. Again, we've got a larger lobe and a smaller lobe. 3 things, they're going to spread out. 3 things spread out and make a trigonal planar. So this is going to be a trigonal planar arrangement. Again, in this drawing, we're not showing the smaller lobe. So H2CO uses sp2 hybrid orbitals. So here we have the carbon with its regular atomic orbitals, and when it hybridizes, it makes sp2, and then there's a p orbital that's left over. So these electrons are going to spread out and have 1 in each. The p orbital is higher in energy than the sp2, but not much. It's one of those things where I'd rather pay a little extra and have my own bed. So they're going to spread out like this.
How come doesn't just form a 2p3 or sp3?
Well, why it doesn't form an sp3 goes back to all the messy math. So, yeah, we're not going to go there, sorry. So here we have oxygen's atomic orbitals. The oxygen is bonded to the carbon, and so this would be a terminal, and we're going to assume that it's not hybridized. So what does it have? It has 2 half-filled orbitals that could overlap with 2 of these. And then we've got hydrogen with a half-filled orbital, and that's going to overlap with these. Okay, so let's look at the Lewis structure. We got 2 fat. Carbon and hydrogen, and a double bond with oxygen. So we're going to see how that double bond forms. But you can see here why oxygen likes to form 2 bonds. Even without hybridizing, it does that. So this is our illustration of the double bond. So let me try to explain this. So here's the carbon, and the purple are the hybrid orbitals. Because the book uses blue for s orbitals and red for p orbitals, and so when you mix blue and red, what do you get? You get purple. So the purple is the hybrid orbitals. So the carbon has these 3 sp2 orbitals, and it also has an unhybridized p orbital. Okay, so it's got this guy up here, and it's got 2 lobes. It's on top and the bottom. Over here we've got oxygen. If we go back and look at oxygen, what's oxygen got going on? It's got this s orbital that's full, and it's got 3 p orbitals. One of them has a lone pair in it, and 2 of them are half-filled. So what we're doing on this oxygen is we're not showing the full p orbital. We're not showing the full s orbital because it clutters up the picture. But we're showing this p orbital, and here's the other p orbital. Right, so that's an orbital, and this is an orbital. So carbon takes its sp2 hybrid orbital, overlaps with hydrogen, makes a bond. It takes another sp2 hybrid orbital, overlaps with hydrogen, makes a bond. Its third hybrid orbital overlaps with one of those p orbitals on the oxygen and makes a single bond. Now, the carbon and the oxygen both have a half-filled, unhybridized p orbital. These are sticking up and down. And what those do is they overlap side to side. So, they're interacting, but they're like bending over to interact. Any questions? This is what's called a sigma bond. It's an end-to-end overlap. These are also sigma bonds, the end of a hybrid orbital overlapping with an s. S can only do sigma bonds. This type of overlap with the side-to-side, that's a pi bond. And you can only get pi bonds by overlapping p orbitals. But that makes the double bond.
Do you know what types of bonds, what orbitals make?
Yeah,
Pi bond, sigma bond.
yeah. We have to learn how to identify pi and sigma bonds. It's not that rough. So what's going on in that molecule is we've got a half-filled p orbital on one atom, half-filled p orbital on the other atom. Those can overlap from side to side. You can have, and that's called a pi bond. A sigma bond is when they overlap end to end. So 2 half-filled p orbitals can make a sigma bond as well. It has to do with their orientation. Do you see how these can both happen at the same time? Because this one's going straight across the middle, and this one's happening above and below that first bond. So we know there's a double bond between the carbon and the oxygen, but there's not room for another overlap like this. So we get the sigma going straight across, and then the pi is the side-to-side overlap. So we use a notation, and you're going to need to do this on the worksheet. We specify the type of bond, whether it's sigma or pi, as well as the type of overlapping orbitals. So this bond here is a pi bond because the orbitals are overlapping side to side. So we write pi and then a colon, and then it's between carbon is using a p orbital and oxygen is using a p orbital. So carbon, p dash oxygen, p. This bond in the middle is an end-to-end overlap. That's a sigma bond. So we call that sigma with a colon. And then from the carbon, carbon's using an sp2 orbital. So we have C, sp2. Oxygen is using a p orbital. And then with the hydrogen, it's a sigma bond. Carbon's using sp2 and hydrogen's using S. This is the Lewis structure, and this is our valence bond model. Any questions? So we get more understanding from valence bond than we do from the Lewis model. A double bond is always two different kinds of bonds. And so when we see a double bond in the Lewis model, now that we understand valence bond theory, we understand that it's a sigma bond and a pi bond. You can't have two sigma bonds. It's going to be a sigma and a pi. Pi bonds are usually weaker. If you think about it, they overlap. There's kind of a strain in their overlap. They can't overlap as well as the end-to-end with the sigma bond. And we observe that the pi bond is easier to break than the sigma bond. And this stuff is going to be important in Chem too. It also explains rotation. I showed you this model earlier, how the single bonds in the model, you can rotate them, right? This bond here is a single bond, a sigma bond. There's free rotation about that. It's an end-to-end, it's symmetrical, and it can just rotate. Double bonds can't rotate. You've got this single bond in the middle, that could rotate, the sigma, but the pi bond is attached at the top and the bottom, and so it can't rotate. And you can illustrate this with your fingers. If you put your index fingers together, you can twist your hands without taking your fingers apart. If you put two fingers together, now you can't. In order to rotate that, you have to break one of the bonds. So that's what's going on with the double bond. Another thing that happens is we see some isomers. Here we're looking at, it's a little hard to tell. This is carbon, hydrogen, hydrogen, chlorine. There's a single bond between the carbons. And so this carbon can rotate, much like this nitrogen on my model. It can rotate around, and so the chlorines can spin around and could be in any position. When you make a double bond, now you can't get any rotation. So that's this model here. There's a double bond, and I can't rotate it around. The green balls are stuck on opposite sides of the double bond. I can't move them without breaking bonds. That's not true with a single bond. So you actually get two different versions of this molecule. Same molar mass, same chemical formula, but they're different and they have some different chemical and physical properties too. What about a triple bond? A triple bond, what happens is you get the s orbital and only one of the p orbitals hybridizing. This makes sp hybrid orbitals. There's only two of them because you're only averaging two, and that leaves two p orbitals unhybridized. So we take the s and the p and we hybridize those, and we get two of these similarly shaped Lobes things one small lobe, one big lobe. They're going to be pointing in opposite directions. They're going to make a linear geometry. So here we have acetylene. I really should change this because what's drawn there is almost the Lewis structure. We're just missing bonds. Here. So what happens here with the triple bond is this. Here's our carbon atomic orbitals, and it's going to hybridize just an S and a P together, and it's going to leave two unhybridized orbitals. So this sp can overlap with a hydrogen. This sp can overlap with an sp in the other carbon atom. And then each carbon has two p orbitals left to form pi bonds. And that ends up looking like this. So here's the carbon with its sp orbitals, one on each side. One overlaps with hydrogen. The other overlaps with the sp orbital on this carbon. They make a sigma bond end-to-end overlap. And this carbon is overlapping with hydrogen, making another sigma bond. Then it's got this vertical p orbital and a vertical p orbital over here. That can overlap in a pi bond. That's the second bond. And then there's this other one that's sticking in and out on both carbons, and that can overlap side to side in a pi bond. And there we have our triple bond. Any questions?
Oh, boy.
Okay.
Watch the slide.
I think we have questions, but we can't put them into words.
Are we gonna have to draw this on the worksheet?
I'm not going to make you draw things like this.
Okay.
So we're not done yet, though. So in the Lewis model, things in the third or greater periods can do expanded octets. And they do this by involving the d orbitals. The second period can't do this because there's no 2d sublevel. It just doesn't exist. The energies of the 3d orbitals are similar to the 3s and the 3p. And so we can pull those in and use them. Okay, so here we've got the standard atomic orbitals, s, p, and d. Well, we can take the s and the 3 p's and pull in a d. And so these are called sp3d. So you'll have 5 of those now, and then these unhybridized orbitals will just be left sitting there. And this is what that hybridization looks like. It's a lot like the balloons. It's 5 balloons. They're going to make a trigonal bipyramid. So here, this arsenic pentafluoride. So arsenic is going to do an sp3d hybridization. You want to see the orbital diagram for that? I'll show it to you if you don't want to see it. So how many valence electrons does arsenic have? 5. So there's D and P and S. 1, 2, 3, 4, 5. Those are the atomic orbitals. But it's going to hybridize. It's going to include a D orbital, and so it's going to make sp3d. So that's going to have 5. And then what's left is there's going to be 4 d orbitals left unhybridized. So that's the d, and this is the sp3d. And then where do those electrons go? 1, 2, 3, 4, 5. They have fillet. Each of these can overlap with a fluorine. On fluorine, fluorine's got S and P. Oops. 1, 2, 3. So this would be the fluorines, S and P. Remember, these are the terminal atoms. We're going to assume they're not hybridizing. They do, but not very much, so we can ignore it. So fluorine has a half-filled p orbital. Fluorine likes to make a single bond. It'll take this and overlap with the hybrid orbitals on the arsenic. And so we'll get 5 fluorines. He saw it. Keep trying, guys. You'll all get it eventually. It's beautiful, huh?
I don't know about beautiful, but it's cool.
It's cool. Okay, we'll go with cool.
Can you say that again?
Can I say that again? Which?
It's cool.
What we're doing with
Okay, I'll explain this from the beginning. Okay, so over here, this is arsenic. Arsenic's atomic orbitals. Arsenic all by itself, right? Its valence shell looks like this. It's got 2 electrons in the s and 3 in the p. When it forms a molecule, it hybridizes some of its orbitals, and it does that to lower the energy. And we don't need to worry about why or how it does that. So it's going to take one of the d orbitals and all 3 of the p's and 1 of the s's, and it's going to mash them together and spit out 5 equivalent energy orbitals. So these were different energies, but it's going to combine them, and now these are all going to be the same in energy. They'll be higher than the s, lower than the d, somewhere in the middle. Then we put those 5 valence electrons in there. There's 5 equivalent orbitals now. They're all going to half fill. There were 4 d orbitals that weren't hybridized. They were empty before. They're still sitting there empty. Okay?
So we just have to put the D even though there's nothing.
I'll show you why or how you should know to put the D in there in a few minutes. Yes?
So, sort of, in general, the valence electrons, in essence, create their own shell. Is that what hybridization sort of does?
Well, they take the existing subshells and remodel them.
But so basically, electrons until then follow the orbitals very strictly.
Right,
Then the valence electrons get together and remodel each other
right.
to make their own.
Yeah, it's, those people staying in the upper floors of the hotel, they've got a little more money, and they're like a little bit wild. They're far from the desk, and they're like, let's break down this wall and put all these beds together.
Did you already go over why some bonds or sigma bonds and some are pi, like how they form, how you can determine which is going to be what?
Well,
Aside from looking at it, can you predict what kind of bond it's going to be?
what we're going to do is we're going to predict whether there's single, double, or triple bonds based on Lewis structures.
Okay.
When you have a double bond in your Lewis structure, there's going to be 1 sigma and 1 pi bond. A triple bond is always 1 sigma and 2 pi bonds.
So just go off that.
We're just going to go off that. Okay. So this is fluorine's orbital diagram. This is a terminal atom, so we're going to assume it's not hybridized. It has a half-filled p orbital. So that's this green one here. It's going to overlap that with one of arsenic's half-filled sp3d orbitals. It has 5 of those, and so it's going to overlap with 5 fluorines. These 5 orbitals arrange themselves like the balloons would in a trigonal bipyramid, and that's why this shape is trigonal bipyramid.
Is it possible to have AsF4? Only have 4 fluorines?
Is it possible to have AsF4? It doesn't look to me like that would be a very stable molecule.
Right.
Because if you hybridize like this, you're going to have an unpaired electron, and if you hybridize sp3, you're still going to have a problem. Yeah.
So I just want to make sure.
Yeah.
So since the p orbital for fluorine isn't completely filled, that's why we fill it up with the other halves from the arsenic.
So the half-filled p orbital is available to overlap.
So the full orbital for the s for the fluorine doesn't really matter. It's just,
No, this would be the equivalent of a lone pair.
okay.
Yeah. So these full orbitals that aren't involved in bonding are lone pairs.
Okay.
And when we draw the Lewis structure, we see that fluorine has 3 lone pairs. And those are the ones. Okay, so,
More.
yeah. It's the last one. It's the last one, I swear.
Huh.
Okay, so an S, 3 Ps, and 2 Ds. So very cryptically, sp3d2. So you're going to get 6 degenerate orbitals and these 3 unhybridized d orbitals. They're empty, they're just sitting there. Well, 6 things do what 6 balloons do. Octahedron. And so something like sulfur hexafluoride would do this. So if we look at the atomic orbitals for sulfur, and this is the sort of thing that we're going to have you do on the worksheet, is you're going to draw, so that's D and P and S. You're going to draw the atomic orbitals just for the valence electrons. How many valence electrons does sulfur have? 6. So I've got 1, 2, 3, 4, 5, 6. So what it's going to do is it's going to cry or bleed. I've been watching a house, and it's like, what orifice is someone going to bleed out of on this episode?
So we take as many from D as we need to put
It-
one in each box?
Take one from S, one from P.
So that's a good question. Do we take as many from here so that we can spread them all out and have one in each? Well, what we're really doing, and we'll get to this, is we're looking at our Lewis diagram and we're seeing how many electron groups are there. There's 6 electron groups, so we're going to hybridize 6 orbitals because we don't want to end up with any lone pairs. So Lewis theory is still very useful. So we're going to take those 6 and hybridize them, and so we're going to get 6, and those are S, P, 3, D, 2. And then you've still got, I'll hide them up there, those unhybridized d orbitals. They're just hanging around. So I've got 6 electrons. I'm going to spread them out here. 1, 2, 3, 4, 5, 6.
Does anything happen with those 3 until D?
No, nothing happens with these.
Because they don't,
Nothing was happening with them here. Those are empty hotel rooms.
they don't actually exist yet, right? Because they don't have any electrons in them.
That's a good question. Do they actually exist since they don't have any electrons in them?
I mean,
They are a function that could be occupied.
potential.
It's a potential place for an electron.
But they're not.
It's like the empty hotel rooms. It's like empty hotel rooms. The room is there, but there's nobody staying in it. So do we care?
It's a hotel room even if nobody's staying.
Right,
Like a tree falling in the forest.
like a tree falling in the forest. Yeah. So each of these can overlap. Yes?
Does that mean that it would have like a net charge, like it would be unstable?
Does that mean it would have a net charge? No, actually it doesn't. We're not changing the number of electrons. We're just changing where they're hanging out. What are the rooms made out of? That's a good question. So in the hotel, right, you've got an S room with with 1 bed, and there were 2 people staying there. And in the P room, there were 3 beds, and you had 4 people staying there. And next door, there's this D room, and it's got 5 beds, and nobody's staying there. And so these guys are getting creative, and they said, let's knock these walls down. We'll move the wall over and stick it up here, leave those 3 beds in that extra part we're not using. And now we've got 6 beds in 1 room. So we haven't made any beds, literally or like tidiness-wise. And we haven't taken apart any beds or made any disappear. It's the same number of orbitals. But we've just modified them. Does that help? Charges don't change because we have the same number of electrons and the same number of protons. We're just changing the shape of the wave function that the electron has. And the reason it happens is to save energy, is to be lower in energy. That's all. So why would a hotel remodel a room? Because they can get more money in the long run by having it that way, right? When these bonds form, it releases a lot of energy. And so that release of energy makes up for the amount of energy that was required to hybridize these. This doesn't happen just spontaneously because they feel like it. You have to put some energy in. but it's the energy released from the bonds forming that makes that happen. Does that help? Any other questions? Yes?
When they hybridize, so previously, their spins are opposing when they're in the same shell.
Right.
So they're hybridized, their spins are all the same.
Right, so here we had spin pair, and here we had a spin pair. And when they go over here, now they're all parallel spins. Electrons can change their spins. They can flip. Just take me at my word on that one. That's complicated too.
Yeah.
Okay, so this has been asked in lecture. How do we know which hybridization scheme? Well, the rigorous thing is you'd look at the degree and type of hybridization. You'd calculate that to give a molecule with the lowest overall energy. We're not going to do that. We're going to go with good enough for Chem 1A.
In 1B, we won't have to do the rigorous?
No, no. In P-Chem, you would get to talking more about the rigorous. The thing is, a lot of these cannot actually be solved. There is no solution. You can just approximate them.
With
Physical chemistry.
Oh, yeah.
Yeah.
That'd be good.
You'd be fine. So good enough for Chem 1A. We're going to assign a hybridization scheme from the electron geometry of the interior atoms in the Lewis structure. So we're thinking about Vesper theory, but really it comes down to the Lewis structure. Number of electron groups on the central atom. Not 100% accurate, but good enough for Chem 1A. And since we're in Chem 1A, we're going to go with that. It's good enough for OChem too, actually. Yeah. Okay, so if you look at your Lewis structure and you see that there are 2 electron groups, you got 2 fingers, 1, 2, sp hybridized. If there are 3 electron groups, 1, 2, 3, sp2. 4 electron groups, got to point at the 4 when I do that. 1, 2, 3, 4, sp3. And this is where I ran out of fingers. So 5 would be sp3, and you've got to bring another finger over d. And 6 would be sp3d2.
So it's SPPP? Is that what you
Mm-hmm. I have sppp
Okay.
because I ran out of fingers. I only have 5 on each hand. Because I'm kind of normal that way, at least. Boring, I know, right? I make up for it in other ways. Okay, so again with the list of instructions. Write the Lewis structure. Use Vesper theory to predict the electron geometry around the interior atoms. Select the correct hybridization based on the electron geometry. Try to do it without looking at table 10.3. Sketch the molecule. Start with the interior atom and its orbitals, showing overlap with appropriate orbitals on the terminal atoms, and then label everything. I'm not going to make you sketch, but I am going to make you label stuff. Okay? So let's do one.
I'm not even order. I'm going to go back to this.
Okay. Okay, so we're going to write a hybridization and bonding scheme for xenon tetrafluoride. The first thing we have to do is draw a Lewis structure. So here's xenon and fluorine and fluorine and fluorine and fluorine. It can be tempting to skip the Lewis structure and say, oh, well, there's going to be 4 electron groups. Maybe not. Xenon can expand its octet. There might be some lone pairs. So we've got 4 times 7 is 28 plus 8 is 36. Right? So we've got 36 electrons. 2, 4, 6, 8. 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. Okay? Got to draw the Lewis structure. We look at the Lewis structure, we see 6 electron groups. That's the octahedral electron geometry, right? 6 electron groups. So we get out our fingers. 1, 2, 3, 4, 5, 6.
SP3D2?
sp3d2. Yep. So the hybridization is sp3d2. Because we have 6 groups, we need 6 orbitals that are the same. Okay? sp3d2. So I'm going to kind of do what your worksheet's going to ask you to do. It's going to want to look at the atomic orbitals for xenon and the hybridized orbitals for xenon. So the atomic orbitals, and again, we're just looking at the valence shell. If you're going to have d hybridization, you really should put the d orbitals in there. 1, 2, 3, 4, 5. Even if they don't have valence electrons in them. So here's S and P and D. How many valence electrons does xenon have? 8. 8. 1, 2, 3, 4, 5, 6, 7, 8. The number of electron groups on the Lewis structure tells us we want to do sp3d2 hybridization. So we're going to take the S, the P, all 3 of them, 2 of the Ds, and hybridize those. So then I'm going to draw those over here. That is sp3d2. And I have to account for these 3 d orbitals that didn't get hybridized. So those are just going to sit over here. They were empty before. They're just going to sit here empty as well. I had 8 electrons here. I'm going to put 8 electrons in here. 1, 2, 3, 4, 5, 6. Now they have to pair up. 7, 8. Look at that. Look, 2 lone pairs, 4 bonds. 2 lone pairs, 4 bonds. Do you hear the angels singing?
I know just my voice in the phone.
Yeah, okay. So this is the hybridized orbitals. This is the atomic orbitals. And then you look at, well, what are the things bonded to it? Well, there's fluorine. Fluorine, we're assuming, is not hybridized, so we just have to look at its atomic orbitals, which we've already done, so I'll draw it in fast. So those are the valence electrons for fluorine. We've got P and we've got S. So it's this half-filled orbital on a fluorine that's going to overlap with one of these sp3d2 orbitals. We look at this and we see we only have single bonds. All the bonds are going to be sigma bonds. So the bonds are sigma, colon. What kind of orbital on the xenon? Which of these is overlapping? sp3d2, right? It's using a hybrid orbital. One of those is overlapping with fluorine, and what's fluorine using?
Wait, back check. Or minus.
No, that's a dash.
Oh, okay, so
It's
we're saying
this
what kind of hybrid?
to this. So it's a sigma, and it's on xenon, it's an sp3d2 hybridized orbital that's overlapping with fluorine's p
So
orbital.
we're looking at what orbital in xenon is.
What orbital on xenon, what orbital on fluorine are making a bond. The Greek letter before tells us, is it a sigma bond or a pi bond? A pi bond is when you have unhybridized p orbitals and they overlap side to side. So that will only come up in a double bond or a triple bond. If it's a single bond, it's a sigma bond.
And since it's the one extra P in the fluorine.
Yeah,
P
it's this guy.
One electron, and that's the one that's going to.
This is the one that overlaps with one of these.
So we're right, okay.
And we need 4 of them to overlap with all 4 of those, and that's why it's as xenon
So that's the
tetra.
bonding scheme right there? That's right after sigma?
This would be the bonding scheme, yeah. This one, there's only one kind of bond, xenon with fluorine, and they're all the same kind of bond, so we don't need to write it 4 times.
If there was a sigma bond and a pi bond?
We would write them separately.
Write them separately.
I think there's an example like that coming up.
Oh, of course there is.
Of course there is. Okay, let's do hydrogen cyanide.
Is this
It's like, you might be tempted to take hydrogen cyanide after this.
serious?
Okay, so we need the Lewis structure. There it is. To figure out the hybridization, you look at the central atom, carbon, and you ask yourself, how many electron groups? No,
One,
not
two,
four.
there's
Two.
the
Two.
three sticking. You're making a face. You knew we were going to say 4.
I knew you were going to say 4. I was trying to warn you not to say 4 by making the face. Okay, this is one group. That's one group. 2 groups. Look, 2 groups. What's the hybridization? SP. See that? I don't just randomly write on my fingers. I did that very intentionally. Okay, so here's carbon's atomic orbitals, right? We got the S and the P. We got 1, 2, 3, 4. So that's carbon. There are 2 groups, 2 electron groups. That tells us it's SP. So it's going to take an S and a P and hybridize them, and then there's going to be 2 P orbitals left over. So those P, and this is SP. This is, these are the hybridized orbitals, and these are the atomic orbitals. When carbon gets into a relationship, when it becomes part of this molecule, that changes it. Okay? It's not the same. It's in the middle of all of this. It gets changed. So we've got 4 half-filled orbitals that can overlap. Let's look at what's going on with nitrogen. This is a terminal atom. We're assuming it's not hybridizing. So for nitrogen, we've got S and P, right? How many valence electrons does nitrogen have? 5. 1, 2, 3, 4, 5. And then we also have hydrogen. I'll just put hydrogen in here. There's a little guy. There's hydrogen. So the hydrogen carbon, that's this hydrogen overlapping with one of these sp orbitals. So that's going to be a sigma bond. This is a single bond, so it's a sigma bond. I'm going to write the bonding scheme way up here at the top. So sigma between the carbon and the hydrogen. On the carbon, what orbital? The sp. And then a dash, and the hydrogen, and what orbital is hydrogen using?
Oh,
S.
hydrogen is it?
Hydrogen only has S. Okay, so I'm going to overlap this one with that one. And then I have another single bond between carbon and nitrogen. This is a triple bond. That means there's going to be 1 sigma and 2 pi bonds. So nitrogen is going to overlap one of its half-filled orbitals with this half-filled orbital on the carbon. So this one overlaps with one of those. So then we can describe that. That's a sigma bond. On the carbon, what orbital is being used? sp. And on the nitrogen, what orbital? P. Well, we've got 2 unhybridized p orbitals here and 2 unhybridized p orbitals there. Those are going to do the side-to-side overlap and make pi bonds. So I'm going to have a pi bond. On the carbon, carbon's using what for its pi bond? P orbital. And what's nitrogen using for its pi bond? P. There's actually 2 of those.
If you just put 2 pi equal, or that, you have to write that 2. Oh, that's 2.
So we've got these guys overlapping, and we've got these guys overlapping. Well, that's why we have to do this today, and we have to work on the worksheet. Because while it's fresh in your mind, if you start doing it, it'll stay. Hopefully.
Lines aren't French toast by now.
French toast?
Lines aren't French toast by now.
I would have said maybe scrambled eggs, but French toast is nicer.
French toast just sounds good.
Does sound good, doesn't it? Use valence bond theory to write a hybridization and bonding scheme for CO2. So I'm going to go through this one kind of quickly, because I'm tired. Okay. So Lewis structure. How many electron groups?
2.
2. Thank
Yeah,
you.
we got it.
2 electron groups. What's the hybridization? sp, right? So we know it's sp hybridized. So I'm going to draw the valence orbital diagram for carbon. Right, it's got S and P. And then I'm going to hybridize. I'm going to have S and P, so that's an SP. And what's left is 2 p orbitals. I'm going to put my 4 electrons in there. 1, 2, 3, 4. And then for the oxygen, I'm not going to hybridize the oxygen. Aren't you glad? Oxygen has 6 valence electrons. Right. So it looks like this. We look at the Lewis structure and we see there's a double bond. That means I have a sigma bond and I have a pi bond. The sigma bond is going to be the hybrid orbital overlapping with one of the p orbitals on the oxygen.
Wait, you said we have a sigma bond and a hybrid bond? Or
A
pi
sigma
bond?
and a pi. A double bond is always a sigma and a pi. A triple is 1 sigma and 2 pi's. Pi sounds good too. So this will overlap with one of these. And remember, those sp orbitals have the same shape, the same geometry as 2 electron groups in Vesper theory. 1 on each side. So it can't use both of these with 1 oxygen, because these are on opposite sides of each other. Here, I'm going to draw this one for you. It's going to be ugly. So here's carbon, and here's, ooh, I should make that purple. Here's an sp, and here's an sp. And then it also has 2 p orbitals that are unhybridized. It's got 1 up and down, and 1 coming in and out of the screen. So it's going to overlap with oxygen on this side and oxygen on that side. Let's just get rid of that. So oxygen has a p orbital that's half full, 2 p orbitals that are half full, right? Looks like a flower. So we're going to get a sigma bond here between a p orbital on oxygen and an sp orbital on carbon. Sigma. Carbon is using an sp, and oxygen is using a p. Okay?
And pi, carbon's using P.
Yep. And for this pi bond, the side to side here, they are both using p orbitals. Carbon, P, oxygen, P.
So that's why we need to include the little P guys up there.
Mhm. So then this oxygen over here, what about him? Well, p orbital, making a sigma bond with the other sp orbital on carbon. So it's just another one of those.
Two.
You could write 2 after it, or you just understand
What
that.
is in chemistry going to move to?
I don't know. And then pi, okay, this pi bond with this other oxygen, it can't use this one. This one's already being used. It has to use this one, right? So this is the Z. That'd be Z. This is X and Y. Yeah, that's Z. So carbon's going to use its Z, pz orbital, to overlap with a pz orbital on oxygen. So it's also coming out like this. And then it overlaps side to side. And that uses the same description. Any question? Clear as mud. I gotta show you this though, because this is, these model kits, they look so simple, right?
So, see, I do have a question.
Uh-huh.
So the sigma and the pi bonds that are notated up there?
Yep,
You've got 2 of each.
got 2 of each. Mhm.
How do you notate that? Say two,
That kind of depends on how the problem's asking you to do it.
What's the test? Oh, you haven't written it.
I haven't written the test yet. That's not for a month. Just think about that. What the book did is, you know, they were drawing the picture, but you guys don't really want to draw the pictures, so drawing the picture, then you would use arrows. Okay, that one's there and here, and this guy and this guy are the pies. You do it like that. Look at this model of carbon dioxide. See how those double bonds work? The double bonds are oriented perpendicular to each other, aren't they? What? So, yeah.
I'm confused on the way because I know.
How did I get the pi? Well, you have to remember that when there's a double bond, it's 1 sigma and 1 pi bond. So the sigmas are end-to-end overlap, and so these hybrid orbitals are going to be used for the sigmas first. And so I used up both of those, making the first bond with oxygen. 1 on one side, 1 on the other. Those can't both be with the same oxygen, right? Because they're on opposite sides of the carbon. So then what do I have left? I have p orbitals here, and I have a p orbital on the oxygen. So one of these makes a pi bond with 1 oxygen. The other p makes a pi bond with the other oxygen. So that's what these red scribbles are.